In this lecture, we're going to talk about telescopes. There are two basic types of telescopes. There's what we call a reflector, and then there's what we call a refractor. Reflectors use mirrors, refractors use lenses. Okay, so we have a reflector, and that uses mirrors, and we have a refractor, which uses lenses. Reflectors are used more often than refractors, and there's a lot of reasons for that I'm going to get into in a little bit. Refractors do have some problems though. One of the problems is chromatic aberrations. Another is the weight of the lenses. So when you're grinding these lenses, they're made out of glass. One, you have to make sure that it's pure. There's no air bubbles or gaps in the glass when you make the lens. The next is the weight. It gets really, really heavy the larger it is, and so you're kind of limited to size. Chromatic aberrations are also caused by the curvature of the lens not being exact all the way around the entire lens. Okay, reflectors and refractors both have what we call spherical aberrations. So chromatic aberrations are where the light enters and it breaks up into its colors, and those colors do not come to the same place as a focus. For spherical aberrations, it's actually the actual shape of the lens or mirror causes problems in where the image is formed. Okay, so here you can see a picture which shows an example of what we call chromatic aberrations. Notice that you get three different images, a blue, a yellow, and a red image. And that's because light will travel at different speeds through glass based on its color. And that causes what we call diffraction or dispersion. It's causing dispersion. It's causing that light to break up into its wavelength components, just like when we talked about the spectrometer. Okay, so let's talk about the disadvantages of refractors. One is chromatic aberrations, which is the light of different colors coming to a focal point at different places. Next, lenses actually absorb infrared and UV radiation, and it's quite severe. And what happens is when that radiation enters, remember ultraviolet's high energy. So anytime you're having light come into a specific part of the lens and it's causing it to heat up, you're going to have that lens change its shape at that location, which is then going to give you a spherical aberration. Okay. Also, again, like I've already said, the lenses become very heavy and they can actually deform under their own weight. The other thing is that when you're making these lenses, you're polishing both sides of the glass. And that means it has to be machined and polished, and it has to be pretty accurate. And so when you get into making lenses, if you're just off by a little bit on one side, it can actually cause a spherical aberration, which means you're not going to see a clear image. It's going to be blurry. There is a limit to the size of reflectors, which are your mirrors. And one of that is the cost. It costs a lot of money to make a really large mirror. It's also a very slow process to make that mirror. And so it takes a really long amount of time. Imperfections are possible the larger it gets. So the larger you make your mirror, the more possibilities you have of imperfections, which will give you spherical aberrations, which will give you a blurry image. Also the weight of the mirror. Not as significant as the lenses. You can get much larger with a mirror than you can with a lens. But you do limit the overall size. So if you want a 20-meter or 30-meter telescope, the weight is going to be an issue, no matter what you use. And again, you can get some sagging due to the weight of the mirror, just like with the lens. Lenses, though, are even more significant. So you're not going to get a very large refractor. So if you see a refractor telescope, usually, I think maybe I've seen maybe a 5-inch, 6-inch, whereas for mirrors, I've actually owned a 20-inch telescope. So you can get much larger with a refractor, but you're still going to have that limit to size when you want to look at things really, really far away in space. Same problem with the lenses. With mirrors, it heats up and cools differently depending on how much radiation is hitting the mirror. That's going to cause spherical aberrations. Okay, so what are some solutions to this problem? One of the solutions, at least for reflectors, is what we call active optics. And what they do is they take these hexagon mirrors and they put them all together to form one larger mirror. And they use computers to actually move these individual mirrors so that if they do start to elongate, they can have coolant running along the mirror to cool it down, and the computers would tell it to do that. Okay, another thing to do is you can also have what we call interferometry. So instead of having one huge large telescope, you could actually build 3 telescopes and look at the same object and add those 3 images together. And that would give you the effective diameter of the spacing between the 3 mirrors. Another thing that we do is computer-controlled telescopes with CCD cameras. CCD is charge coupled device. And so basically it's this little tiny chip. They have electrons that are charged on the surface. When a photon comes in, it causes those electrons to cascade. That cascade of electrons comes out as a current. That current is then measured by the computer, and that tells you, the amount of current will tell you the equivalence in photon energy. So that it's sort of like taking a digital picture. Okay, so what I'd like to do is cover first visible telescopes, which cover the visible range of the electromagnetic spectrum, and then we'll start talking about others. Okay, so one of the visible wavelength telescopes is the European Southern Observatory, or the ESO. This is located in Chile, and it has a 16-meter effective diameter, so that's fairly large. It is actually 4 individual 8-meter diameter mirrors that look at the same object at the same time, and that gives us an effective diameter of 16 meters. The next one we're going to talk about is the McDonald Observatory, which is the Hobby Eberly, and that's located in Texas. It's an 11-meter diameter. The effective diameter is 9 meters. It's actually made of 91 hexagon segments that, again, are controlled independently of one another with a computer system. Oh, these are my favorite. These are the Keck telescopes in Hawaii. And oh, I would love to visit them. They're 2 10-meter diameter, effective diameter telescopes. They are made of 36 hexagon segments, which are each 1.8 meter wide. I don't know if you know what a meter looks. A meter is about the size, a little bit longer than a yardstick. So take 1.8 yardsticks, and that's 1 hexagon segment. And then take that and multiply by 36, and that's how many you have. This thing is incredible. 10 meters. Okay, the other one is the NOAO, which is located, there's actually 2. One's in Chile and one's in Hawaii. And it has an 8-meter effective diameter. And again, this is using active optics. Now let's talk about, let me just say this. There are many more visible telescopes nowadays, and certainly you can get your own. If you're going to get your own visible telescope, I strongly recommend that you not go with the fancy schmancy base where it auto aligns with the stars and follows them tracking. I mean, yeah, that's great, but you have to actually program it to do that. And I had one and I threw it out. I'm just going to let you know, it was a lot of effort to just see some stars, which I could see with a pair of binoculars, so I didn't use it. The most effective telescope I have ever had is, and it can be any size, it has a Dobsonian mount, and this thing is so simple. Basically, the telescope sits on a pad that can rotate the telescope up and down like this, and then it's on a swivel base that rotates. So you rotate it, you swivel it. Okay, very, very easy base to use. No control necessary. It doesn't wobble around. If you break one of the metal clamps in the middle, there isn't any metal clamps, so you can't break it. They're usually made of wood, the Dobsonian mounts. I love them. They are the easiest telescopes to use if you're going to be, if you're just starting out. The other thing I recommend, pair of binoculars. Get yourself a nice pair of binoculars for the price that you would spend on a telescope, and you can see just as much. I can see the Orion Nebula with a pair of binoculars. I can see the Andromeda Galaxy just as well as I can with a 10-inch telescope. Okay, so get yourself a pair of binoculars. It's easier. You just, there it is. There's the moon. You look, and there it is. Okay, very easy to line up. It's great for amateurs to start out and just see what's out there. Okay, so now that I've gone off on my little tangent about telescopes and binoculars, let's talk about radio telescopes. Carl Jansky at Bell Labs in 1931 was the first to develop a radio telescope. He's known as the father of radio astronomy, or at least one of the fathers of radio astronomy. So why have radio telescopes or radio astronomy versus visible? Okay, well, if you look at the places that the visible telescope observatories are located, they're probably on mountains up really high away from the atmosphere. And here's why. If it rains, you can't see anything. In the daytime, can't see anything. So they're very weather and temperature dependent, and they're also seasonal dependent. The more water vapor you have in the air, the harder it is to use a visible telescope. Radio telescopes, though, do not have those same problems. So, one, you can use a radio telescope 24 hours a day. So I've even had students that have made their own. You take an umbrella and you cover the inside of it with aluminum foil, and they've been able to pick up radio waves with that. You can see through clouds. So if it's a cloudy day, guess what? You're still observing. You don't need to worry about packing it up. Also, radio telescopes allow us to see things that we can't see in the visible range. So with radio waves, we can start seeing those dust clouds. We can start seeing more outlines to the Orion Nebula that you can't see with your visible telescopes. And so some examples are clouds of cool hydrogen. We can also see what we call active galaxies. Active galaxies are galaxies that look like normal galaxies with a regular telescope. But when we look at it with a radio telescope, we see these these jets of energy coming out of the center of these galaxies. It's quite astounding looking. Okay. Also, the nice thing about radio telescopes is they can go anywhere. If you're out to sea, it's a little bit more complicated. You have to actually correct for the motion of the waves, which I don't recommend. So you can put them in South America, you can put them in the United States, you can put them in Canada, you can put them in Antarctica. Radio telescopes can pretty much go anywhere. There is a disadvantage though, and that is that they're very weak signals that come in from space. So in order to pick up as many signals as possible, you have to make these telescopes as large as possible. And that's where it gets a little bit complicated. How do you build such a huge telescope to be able to pick up these signals? Okay, so you need a large telescope and a lot of space to hold it. But there's ways. We are human beings and we are ingenious. We've come up with ways to fix this. We have developed what we call an interferometer. Just like with having 3 telescopes measuring one spot in space and adding the 3 together to give us an effective diameter, we can do the same thing with radio telescopes. We can have a whole bunch of them lined up at the same object, add them together, and that gives us a better signal. Okay, now look at this. Isn't this huge? This is a large radio telescope, the largest. It's in Russia. Isn't that beautiful? And it's like on the ground, like there's grass growing in this thing. The diameter of this telescope is 576 meters. Huge. This one is actually one of my favorite radio telescopes. There's 2. This is the largest steerable radio telescope, and it's located in West Virginia at Green Bank. And in fact, at Green Bank, that area, I don't know if it's still the case, but back 10 years ago, that whole area was gridded off. You couldn't even have a cell phone in there because it would disrupt the telescope. I don't know if that's still the case, but I can't see that they wouldn't still have a limit on the waves. I mean, basically radio waves, microwaves, none of that can be there because the telescope will pick it up. But this is the largest steerable, meaning that you can actually shift this and move it. The diameter is about 100 meters and it stands higher than the Statue of Liberty. Very, very impressive. Okay, here's my next favorite. This is Arecibo in Puerto Rico. I just love the look of this telescope, and this is the one that SETI is using, the Search for Extraterrestrial Intelligence. They use data off of the Arecibo telescope, and if you download an app, I think, or there used to be a computer program you could have on your computer, you can analyze little bits of data from the telescope, and it sends it back to SETI. If everybody were to do that, we would be able to have most of the data analyzed in a reasonable amount of time. As it is, with one computer or one supercomputer, with all the data we're collecting, it would take 10, 20, 30, 100 years to get through all that data. So if you have some bandwidth available on your computer, or there's times when you're not using your computer, but you keep it on, and you want to download that app, go ahead and take a look at it. It's for SETI, S-E-T-I. Okay, this one is in New Mexico, I believe, or Arizona. We'll check in a minute. This is called the Very Large Array. It's actually New Mexico. It's actually multiple radio telescopes in a like a Y configuration where they all add up to give you a diameter much, much larger than the individual. If you've ever seen the movie with Jodie Foster called Contact, that's the telescopes that she's using in the movie. Okay, there's actually 27 radio dishes. And again, they make a Y-shaped set of tracks. And again, you have to put in grant money and put in for time to use the telescope. Now, radio telescopes are great. Visible telescopes are great. But what would make them even better is if we didn't have to worry about the atmosphere. And there's a lot of radiation we can't see. So for instance, it's really difficult for us to see X-rays and gamma rays on the Earth. Our atmosphere blocks out a lot. It also blocks out infrared radiation as well. And so does glass. So it makes it kind of hard for us to see when quite a bit of radiation that is coming from space is being absorbed and scattered by our atmosphere. So now we're going to talk about space telescopes and their importance. I'm not going to cover all of them. Keep in mind that as technology advances, telescopes will also advance. There's more and more telescopes out there that are wider, larger, collecting more data, analyzing it faster, but it's just too difficult for me to keep up with it, and we would be here for a year just talking about telescopes. So I can only just give you a glossary look at some of the big name telescopes in the past and currently. Okay, so again, some of that radiation is absorbed by the atmosphere, so we've put telescopes in space. All telescopes can see the entire electromagnetic spectrum. Notice I said all. That doesn't mean your refractor will see gamma radiation. What I'm saying is all the different types of telescopes radio telescopes, visible, infrared, gamma ray telescopes, we can now look at the entire electromagnetic spectrum with a telescope of some kind. Okay, so this is done. One of them, and I think they've had more since then. This is called COBE, which is the Cosmic Background Explorer. This was actually the telescope that took measurements of the background radiation and microwaves. And we were able to determine the background temperature of the universe to be about 2.7 Kelvin, which is actually predicted by the Big Bang Theory. We measure cold, dark dust clouds with the COBE. Okay, for infrared telescopes, we have Spitzer. This can actually look at planets, and actually one of the newer ones is the Kepler probe. The Kepler probe has found many, many, many habitable planets. So if you want to take a look at that one for your discussion, you can also look at Kepler. Spitzer also looks at comets and the formation of stars. So this is going to go low temperature because it's infrared. Space telescopes in the visible range, the most popular and well known is the Hubble Space Telescope, the HST. This has a 2.4 meter diameter mirror, and there were some spherical aberration problems with this mirror. They actually knew about this before it was sent up, but there was some miscommunication. It got sent up anyway. There is another mirror here on Earth that's been here the whole time, and they've been using that to help to correct the cameras for the HST. The HST has had multiple repairs done to it, or multiple additions of cameras. There's the far field camera that was just added. Not just added, it was added like 10, 20 years ago. When we ended the Space Shuttle program, we ended our maintenance to the Hubble Space Telescope. So we will no longer make fixes to the Hubble. When it stops working, we're done. We no longer have information coming from the Hubble when that happens. And again, this was unique for being in space. And again, the advantage is it's not affected by the atmosphere. For the UV radiation, we have the Hopkins UV Telescope project. This included 2 telescopes, Astro 1 and Astro 2, and you see pictures of them. And they learn about hot stars and also hot gases. So anytime you have star formation occurring, you can look at it with the UV telescope, and that'll tell you about the hotter parts of the formation. Okay, here we have an X-ray telescope, which was Chandra. And with Chandra, we learn about very hot regions in stars. We also learn about violent events such as supernovae, and also the formation of neutron stars and black holes. For gamma rays, this is kind of a difficult range to actually collect data on. We have the GLAST, which is the Gamma Ray Large Area Telescope, which was in 2007. This telescope could tell us about black holes and neutron star formation. Again, exploding stars, erupting galaxies, galaxies that are colliding with one another, and again, neutron stars and their formation. And